search and bounds, part 1. In this session, we will have 2 papers. The first one is entitled Differential Trail Search in Cryptographic Primitives with Big Circle Key. The authors is Alireza Mahadad, Jan Diamond, Lorenzo Grazzi, Sylvia Mala. Alireza will give the presentation. Welcome.
Yeah. Can you hear me? Hello.
Yes.
Okay,
Yes.
okay, good. Thanks for the introduction. The title of my presentation is Differential Research in Cryptography Primitives with Big Circle Key. And this is a joint work with Sylvia Mella, Lorenzo Grazzi, and Yuan Diamond. First of all, a quick introduction. Differential cryptanalysis is one of the most powerful and well-known cryptanalysis. The main idea is to, so let's say we have an algorithm that has all round, the cryptography primitive that has all round, and then as input we give M0 to it, and it computes the value C0 at the output. And let's say we do the same scenario for another input M1, and it computes C1. Then the difference between M0 and M1, let's call it delta 0, and the difference between C0 and C1 at the output, let's call it delta R. Then we can say that the security that this primitive provides against differential attack is upper bounded by the probability that this delta 0 goes to delta R. This is called differential probability. But it's hard to determine this value. In order to determine this value and make it easier to determine, we divide this R round into R separate rounds. Then we will have something that is called differential trail, and it means, so we show it with QR, and the goal is to go from delta 0 to B1 after 1 round, and from B1 to B2 after 2 rounds, and so on. Then we can say that under some assumptions, the differential probability of this differential trail is equal to the dp of delta 0 goes to B1 and B1 goes to B2 and so on. Then we can say that, yeah, again, under some assumptions, we can say that dp of delta 0 goes to delta R is almost equal to dp of this differential trail. I have to introduce one term that I will use in this presentation, and it is called weight. And the weight of a difference bi goes to bi plus 1 is equal to minus log 2 of dp. And it is just for simplicity, and it means that, for instance, instead of dp equal to 2 to the power minus n, we just simply say that the weight is n. Then we can conclude that the weight of a differential trail is almost equal to the weight of delta 0 goes to B1, and the plus the weight that B1 goes to B2, and so on. And so because the title of my presentation is Differential Trail Search in Cryptography Primitives with Big Circuitry, I have to also explain what is Chi function. So this is how a Chi function looks like. In order to compute each bit of the output, we need to know the value of 3 bits of the input. We compute the NOT of B1 and AND it with B2. And then the result will be XORed by bit at position B0, and it gives us the value of A0. We do it for all bits of the output in order to get the output values. If the value of n is big, we say that this Chi is working on a big circle. And by big, I mean like for subterranean. So the application of my work is on subterranean, and for that the value of n is 257, which is a big number. Okay, Let's talk about generating all-round differential tray. So this is how an all-round differential tray looks like. This is the input difference and this is the output, and these are the differences after each round. Okay. Each round of the modern ciphers can be divided into two layers. So the nonlinear layer that is called in this paper is called chi, and the linear layer that is called lambda. I just copied the differences after each round, and we can call the differences before linear layer AIs. Then the dp of, so it's known that the dp of AI goes to bi over a linear layer is equal to 1 or 2 to the power 0, then the weight is equal to 0. So the only thing that we need to compute in order to compute the weight of a trail, a differential trail, is just computing the weight over nonlinear layers. And the goal of our work is to compute this for an all-round trail. But it's not efficient to start with all-round trail. So in order to do it more efficient, we start with two-round trails. So the reason is explained in the paper. This is how a two-round trail looks like. Since chi function has degree 2, the weight is determined by just its input, and it is also mentioned in one of the references of our paper. Then the weight that was computed like this in the previous slide can be we can simply write it as this one, which is just so the input of chi is bi and bi plus 1, so we can just simply write it like this one. And we can also ignore the value of ai plus 2 and bi plus 2 in this formula, because the only thing that we need to compute the weight of these two-round trails is bi and bi plus 2. So we can ignore this part. We can remove it and just generate this part. And another thing is that I have to define is minimum reverse weight, which is the minimum over weight of all BIs that are compatible with AI plus 1. So if we generate all BIs that are compatible with AI plus 1 and compute the minimum weight over all of them, then it's called minimum reverse weight. And in this paper, we introduced a new method to compute this value. It allows us to ignore BI also. So if we can find a way to compute the weight of this, the weight based on AI plus 1 and BI plus 1, then we don't need to compute this. This leads to introducing a new thing that is called two-round trail core. It's not new, we didn't introduce, but yeah, this is two-round trail core. And this is how it looks like. So the goal is to generate all these two-round trail cores up to a specific weight. In order to do that, we generate all A1 values, and then we compute B1 based on the value of A1, which is just lambda of A1. And then if the minimum reverse weight of A plus weight of B is smaller than T2, which was our bound, then we say that this two-round record is a valid two-round record. But how to scan the space of all two-round records up to a certain weight T2? In order to do that, we use the tree search approach that was used also in a paper of Mela et al. In TASC 2016. And the way that they generate and we generated our tree was the same. Each node of the tree represents an order list of active bits at A1 and its corresponding active bits at B1. Three functions were used in order to visit all nodes of the tree. The first function was toChild function that adds a new active bits to A1. ToSibling function that changes the last added active bit of A1 and two parent functions that deletes the last active bit of A1. Here we should again introduce another term that is called score. It is a lower bound on the weight of a node and all its descendants in the tree. If we can have such a bound, such a lower bound, this allows us to prune the tree. It means that if a node and all its descendants have like a weight higher than our budget, we can simply ignore them and do not go into that branch of the tree. It leads to a faster scan of the tree, or equivalently, at the same time, it leads to scanning a larger space. Score can be defined separately for A1 and B1 here, because we said that in our paper, we introduced a new generic method to compute the score at A1, and also a new method to compute the score at B1 for subterranean. The reason that is not generic is that the score at B1 really depends on the properties of linear layer. So yeah, it differs for each cipher. And then let's say we have all 2 round trade cores, and but the goal was to generate all round trades. In order to do that, we need to extend the thread. So this is a 2 round thread core. In order to extend it, we extend it in both directions. Forward extension, we generate all A2s that are compatible with B1, and it is known how to do that. And then we can simply compute B2s because there is only one linear layer and it can be computed easily. For backward direction, for backward extension, we introduced a new method to efficiently generate all B0s that are compatible with A1. In our paper, we introduced that. And then we can simply compute the value of A0s. But what is the application? So first of all, a quick motivation. So this is the FPGA benchmark of NIST lightweight competition of round 2 candidates of this lightweight competition. As you can see, I just copy pasted this figure from this reference. As you can see, subterranean is here. It means that it has the lowest energy per bit amongst all round 2 candidates that are listed here, with specific message length and frequency. And also, yeah, so this is maybe it's interesting. The ASCON is here. This is the winner of this competition, and it was also one of the best. And also for throughput over area, again, subterranean was one of the best, and the winner of the competition, ASCON, is also here. But how does it look like? This is the subterranean round function. I explained how he works. So this is the only non-linear layer that this function has. And then we have a iota function that is a simple NOT gate here. And then we have theta function that adds 3 bits at position I plus 3, and I plus 8, like here, adds them and computes 1 bit at the output. And then after all, we have a pi function that maps S12I to Si, like this. Okay, so the goal of our work was to scan 8 round trade cores in subterranean. And the reason that we choose 8 round because all 3 primitives of subterranean had this 8 round in their algorithm. In order to do that, we scanned all 2 round trade cores up to weight 28, all 3 round trade cores up to weight 40, and all 4 rounds up to weight 57. But for this part, we didn't find, there is no trade core up to weight 57. It means that The best 4-round records that is possible has weight 58, and that is exactly what we found in our trace search. And in the worst case, 2 4-rounds with weight 58 can be compatible with each other, and they can form an 8-round trade core. It means that in the worst case, we can have 2 4-rounds with weight 58, that if we add their weights, then the weight of an 8-round trade core can be at least 116. And based on this work, we could prove a bound, a new lower bounds that are listed here. And it allowed us to like improve the lower bound on the weight of 8 rounds by 18, or equivalently, it means that we scan 2 to the power 18 bigger space. As a conclusion, we introduced a score function. In our paper, we introduced a score function that lower bounds the weight of a 2-round trade core and all its descendants during the tree search. We introduced a method to efficiently compute the minimum weight of a trade core, a method to efficiently perform backward extension, a software tool for differential trace search tailored for subterranean, and that allows us to define a new, to find a new and more precise lower bounds on subterranean. At the end, we can say that the tree search is a very strong and useful tool that can be used for both designers and attackers. Thanks for your attention, and I would be happy to answer your questions.
Any question here in Beijing? Okay, any question in Kobe?
Yes.
Hello, can you hear me?
Yes.
Yeah.
Yeah, I noticed that you scan the differential track core for 2 rounds, 3 rounds, and so on. I wonder, have you found a differential rather than a differential trail, which will have a larger probability?
I didn't get the last part of your question, sorry.
Can you get it?
Sorry?
I wonder that, have you found a differential rather than a differential trail, which will have a larger probability?
Yeah, so I didn't get the last part, but the thing that we did was to scan the differential trail, but not the differential. I don't know if it answers your question. No?
You found a larger differential to, which will have a larger probability, yeah. I mean that not a differential trail. It's a differential.
No, they are differential traits. I am sorry.
Do you mean the clustering effect?
Yeah.
Yeah.
No. It's just so for 2 rounds we scan the whole space, but for more than 2 rounds, so let's say we go to 3 rounds, or we want to extend the trade, then we don't do that. We just scan differential trails, but not differential.
Okay. Thank you.
Yeah. Thank you.
And one more question in Kobe. Please.
Yeah. Hi, Alireza. I would like to ask a question. So is there any of the methods you introduced in this work that could be used to the work of 2016 to improve the bounds on Keccak?
Bounds on Keccak. So the design of Keccak, I assume you know that it uses He5. That means that the circle that He5 was working on had only 5 bits. So it means that many of these parts, for instance, completing a score can be like, you can exhaustively search 2 to the power 5 possibilities in Kecheck, and you don't need to have a score function that is working generally. And also, something like a backward extension that we introduced it for big circle key because it's not possible to do it exhaustively, but in Kecheck it was just 5 bits, so you could exhaustively search all of them. And this port is just application, and this port this is again for this big circle key, but for small circle key like Kecheck or Zudu, you can exhaustively search that. So it's not needed. But the main focus of this paper was to see how it works for big circle key.
Okay, that's very clear. Thank you. Well, thanks.
Okay,
There is another question in Beijing.
Hi, thanks for the talk. I was just wondering how easily could this technique be applied to other ciphers, and also if the code's available for use?
Thank you for your question. The codes are available, and so you can find it in the paper where you can find the codes. It is not that easy to apply it to a new cipher. If you just want to design a new cipher completely different, then you have to write these codes from the scratch, I would say. But the limits that you can reach is higher than the general method that we have, like MIP or SAT solver.
Thank you.
Thanks.
Okay, thanks, Leda. Let's move to the next paper. Okay, the next paper is entitled Accelerating the Best Trail Search on AES-like Ciphers. The authors are Songjin Kim, Dak-Jong Hong, Jaeshou Song, Saki Hong. Songjin Kim will give the presentation. Welcome.
Thanks for the introduction. As she said, I'm Songjin Kim. I'm from Korea University. I'm going to talk about accelerating the best trail search on AES-like ciphers. So, So starting with the introduction to our contributions, I will present 2 accelerating strategies and show the analysis result on gift variant, which we call bogey-based ciphers in the paper. So the first contribution is accelerating the best trail search on AES-like ciphers. So basically, we accelerate a matrix search algorithm with 2 strategies. One is giving strict pruning conditions to the search. We derive them by using the structure of AES-like ciphers. And another, reduce the search space by employing permutation characteristics in the trail search. We applied both our strategies to the existing ciphers and demonstrate the improvement. So here are the search results. Above our improvement gave us the first analysis result on full round gift 128. And differential and linear trail search on gift 64 take only in a second and 10 seconds respectively. And we expect that our implementation can be also used for other AES-like ciphers. Our code and analysis result can be found in this repository below. And another contribution is investigating if the variance in terms of DC and LC resistances. We devise gift variance by replacing the existing S-box and bit permutation. The number of such variants at first, the number of such variants amount to 2 to the power of 37, which is infeasible to analyze. So we reduce the number by deducing equivalence relation and obtain their representatives. With our search algorithm, we obtain the minimum required round for such representative gift variants with several block sizes. According to our search result, we can show that there exists a gift variant allowing fewer rounds than gift to prevent effective differential and linear trails. So before presenting our accelerating strategies, here we define AES-like cipher. An AES-like cipher consists of identical round functions, and the round function consists of S layer and mixing layer and shuffle layer. S layer applies identical S boxes, and mixing layer applies identical matrix multiplications. Lastly, shuffle layer shuffles S boxes, which implies S layer and shuffle layer are commutative. And depending on whether matrix multiplication is a bit permutation or not, we call them bit permutation based and non-bit permutation based AES-like ciphers. So for example, this slide shows that present and gift are bit permutation based AES-like ciphers. So for a better explanation, I will use weight rather than probability. Weight is the negative logarithm of probability of the trail. And when you talk about this minimum required round, that means the corresponding best weight should be equal to or bigger than the block size. And now I will briefly introduce Matsui's search algorithm. This search algorithm is a branch and bound depth first search and requires the knowledge of these 1 to R minus 1 round best weights when we search for R round best trail. So here is the, even though this algorithm is an exhaustive search, those given best weights can provide pruning conditions that we can efficiently prune the trails just before arriving at the final depth. So here is the application of pruning conditions to 8-round differential trail search. Assume that we just determined differences until 3 rounds. Although we don't know Although we don't know the weight of this undetermined part, the given 5-round best weight can replace the weight, so that we can decide whether we go further or not only in the middle of the search. Instead of applying these pruning conditions round by round, we can apply them S box by S box. These more frequent applications make this left side of the pruning condition bigger, and this search terminates faster. So in this regard, we try to make the left side bigger by using the structure of AES-like cipher, and this middle part more. So first, we decompose the round function into the corresponding components and change the order of S layer and shuffle layer. Then we get, in this figure, we get 4 independent super boxes to deal with. Assume that we just determined 7 S boxes in this first S layer. then the green shaded input part can be determined now. And blue shaded part has the lower bound for the number of output active S boxes according to the first S layer's active S box pattern and the branch number of matrix multiplication. Now we can partition this middle part into the corresponding 4 subparts and obtain strict pruning conditions for AS-like ciphers. Among these subparts, this subpart 4, which is green, blue shaded, is more effective when the branch number is bigger. That means for bit permutation based AS-like cipher, that the subpart 4 might not be effective. But however, we can use the property of bit permutation, which is even partial input can provide the lower bound for the number of output active S boxes. So we can further consider subpart 4 prime and obtain stricter pruning conditions for bit permutation based AS-like ciphers. And another accelerating strategy is employing permutation characteristic. As we will see, one permutation characteristic ensures that 2 different trays has the same weight. This figure gives the concept of how we employ a permutation characteristic in tray search. Over these components, for any sequences of values, there must exist the corresponding word-wise permutative sequence which have the same weight. This is because, as I mentioned, the S layer applies identical S boxes, and we just use word-wise permutations. So after tray search with an input active S box pattern, we don't have to consider any trace from the corresponding word-wise permutative pattern. So formally, R1 permutation characteristic is defined as a sequence of word-wise permutations such that the permutations are connected between rounds. Since our round permutation characteristic only covers such T-round tray search, we need iterative ones for the arbitrary round search. So in order to obtain iterative permutation characteristic, we generate a directed graph according to permutations over one round and obtain cyclic subgraphs. So figures on right side gives the directed graphs of our considered ciphers. So on each of them, we obtain cyclic subgraphs, which are equivalent to iterative permutation characteristics. So here are the iterative permutation characteristics of our considered ciphers. The number of word-wise permutations on iterative characteristics is up to 16, and the search space decreased by the same amount of vectors. So we conduct comparison without our strategies when the first strategy only used the acceleration is up to 500 vectors, and the second has the acceleration 10 vectors. And when we apply both strategy, when we apply both strategies, the acceleration is up to about 2000. So for a more in-depth application of our search algorithm, we use our the algorithm to investigate ciphers based on bogey design. So for bogey design, we need a proper combination of S-box and bit permutation, and each combination constructs such these 16-bit superbox and prevent single active backbit propagations, which are also known as bad and bad connections. Such combinations amount to 2 to the power of 37, and we can construct the corresponding 16-time bit bogey-based ciphers with a proper shuffle layer. So that means we need to conduct the investigation with the same number of ciphers. So this number is infeasible to conduct the investigation. We reduce the number by deducing 3 equivalence relations between superboxes, which means we don't consider shuffle layer here. So the number of ciphers with different block sizes is the same. And after 3 equivalent relations are applied, the number of representatives is about 41,000. And we applied our strategies to those representatives and obtain the minimum required round. And this table gives the information about our search. And we chose this analysis round, considering the minimum required round for gift and analysis time. According to our search, we can show that there exist better combinations than gift. And we remark that only replacing bit permutation can even allows fewer round to prevent effective differential and linear trace. This table gives that result. And this slide gives the best ways of 16-4-bit versions and comparison with gift 64. The red line represent the best weight of gift 64, and blue one represent the weight of 64. And this slice gives the best weight of 120-bit versions. Due to the increased analysis time, we conducted the search until 11 round. Although it is not enough to obtain the minimum required round, we could show that the 11 round optimal combinations require 3 fewer rounds than give to 128. So this concludes my presentation. As I previously mentioned, our implementations and codes and analysis result can be found at this repository. So thank you for listening.
Thank you. Thanks, speaker. So any question in copy?
One question in copy.
Okay.
Thank you for your talk. I was wondering, when you tried different type of bogey permutations for gift, you tried with only gift S box or different type of S boxes? Okay, okay. Okay. So for the best result, which S box you used?
Sorry?
Yeah, for the best result, which S box you used?
Different from the existing S box. So actually, we try to evaluate the cost of S boxes because it is important when we implement that that algorithm in hardware. But we did it, but sometimes there is a trade-off between cost and this resistance. But we couldn't write down the result on that paper.
Okay, so is the S box is given in the paper or?
Oh yes.
Okay, okay, thank you.
You can find any result in the repository as well.
Oh, okay, thank you.
Okay,
Any questions? No questions in Kobe,
Okay.
it seems.
Any question in Beijing? Here? Okay. Any question online? Okay. If there is no question, let's end this session. Thank the speakers again. Let's have a break.